day 5, and this will be the last session. The title of the talk will be non-linearity. The speaker is Dr. N. Selvaganesan from IIST, Department of Space, Government of India. Now I'll be introducing him to you. N. Selvaganesan received his BE in Electrical and Electronics Engineering, ME in Control Systems, and PhD in Adaptive Control System from NEPCO Shillong Engineering College, Shivakasi, PSG College of Technology, Coimbatore, and MIT Campus, Anna University, Chennai, in the year 1997, 2000, and 2005, respectively. He has more than 20 years of research and teaching experience at MIT Campus, Anna University, Chennai, Pondicherry Engineering College, and Indian Institute of Space Science and Technology, IIST, Trivandrum. Currently, he is working as a professor of Department of Avionics in IIST, Trivandrum. He has been served many administrative positions at IIST and other institutions, universities, which include Head, Department of Avionics, IIST, during 2013 to 16. He has 38 peer-reviewed international journal papers and 45 conference papers to his research credit. He has completed 3 research projects sponsored by ISRO and DSTE in the field of modeling and control. His current research direction is towards human health monitoring and fault diagnosis of crew module flight control in space. He has been involved in many editorial activities, reviews in various international journals, conferences, and workshops in control system design. His areas of interest include control system design, estimation theory, biological modeling, fault diagnosis, and fractional order control. He is senior member of IEEE. So this is about the speaker. I welcome you, sir, in this Atal FDP. I'm glad that you have agreed to be the speaker, one of the speaker in this Atal FDP. Now I'll be introducing you to the participants. There are total 200 participants who have registered for this Atal FDP, out of which 25 participants are from Andhra Pradesh, 46 are from Tamil Nadu, 10 from Karnataka, 13 from Uttar Pradesh, 24 from Maharashtra, and from all other states there are less than 10 participants. So the participation is from all over the country. The participants are from various fields of engineering. Now I welcome you, sir, again, and now over to you.
Thank you, ma'am. Thank you for the introduction, and nice to hear that there are many participants across the. So thank you. Nice to hear that across the country, maybe around 200 participants are there actually in this workshop. So before starting the lecture, I would like to thank you and the institute for giving this opportunity to present the maybe a part of research work which we carried out some time back. So, but we are not going to discuss much in research level. We are going to discuss much in fundamentals. Can you please enable the sharing thing so that I can able to share? So right now it is disabled. Okay, so the topic of interest today, presentation today is non-linearity. So far we heard many things with respect to measurement systems and control systems, because instrumentation maybe is the front end of control systems, right? So either instrumentation side, most of the time instrumentation side only creates non-linearities. Okay, we are going to see the non-linearities which are introduced by the devices which we come across maybe in engineering applications, and how these non-linearities are normally handled in control system design. So this is the topic of our interest today. And just before moving on to that topic, I would like to thank the organizer again to give this opportunity to give a presentation about this title, non-linearity. The objective of the presentation is as follows. So this objective of the presentation is as follows here. We would like to introduce something about what is non-linearity, that is properties, issues, and analysis. And majorly we are going to concentrate on how these non-linearities are analyzed, will be analyzed using the function, describing function we call it as. So that is the one. And with some examples like on-off relay and relay with dead zone and backlash, because these are the non-linearities most of the time occurring in the either in the feed forward loop or in the feedback loop, like sensors and other part of the closed loop system. And we also going to discuss about something about the fundamentals about stability, how the stability is analyzed. In first, we would like to start with the linear system. Then later, we would like to understand in the presence of nonlinearity how that stability is. So finally, we are going to use this tool for showing that how that nonlinearity is that predicted. So because when the moment you get into the nonlinearity, we always get some kind of limit cycle. We call it as limit cycle. We will discuss in detail in the next slide, upcoming slide. And finally, we are going to show with some case study with some system with some nonlinearity like relay with the dead zone. And another system we consider as a practical system is a servo system with backlash. So this is the way which where our presentation is going will be quoted. And let us start with linear systems, because these are all very familiar to all of you, because since we are a faculty member or maybe doing a research level in the area of measurements and control. So when you talk about linear system, right, the x dot equal to ax, it is basically a system I'm representing in the form of state space. So suppose the state space model x dot equal to ax has unique equilibrium point if A inverse exists. Because normally linear system consists of only one equilibrium point, unique equilibrium point. So suppose if you say that A inverse doesn't exist, that indicates that the system is having multiple equilibrium point. That actually represents that say that the system is said to be nonlinear. Yes, and second point is we defined. So if A inverse doesn't exist, what will happen? Infinite number of equilibrium point exist. So that indicates the system is said to be nonlinear. Then all equilibrium points are stable regardless of the initial conditions. In the presence of external input U of t, the system response has the following properties. So suppose if you talk about equilibrium conditions, stable equilibrium conditions, right, with some initial conditions. Okay, so it has to satisfy the property. The property number one is a superposition property. So we know that with the superposition property, it should satisfy the homogeneity and additivity property, which is shown in the figure here. And the second one is asymptotic stability, right? So asymptotic stability. So normally we talk about the notion of stability in two forms. One is bounded input, bounded output stability, and second one is asymptotic stability. So bounded input should provide bounded output. Asymptotic stability normally system is with respect to initial conditions. If the system is driven by the initial condition, that output should be tending to zero and t tends to infinity. This is what we normally say that asymptotic stability. So as basically asymptotic stability is the broader class actually. So if the system is said to be asymptotically stable, then it is by default it is Bigos stable, but reverse is not true. Okay, so and third important property with respect to linear system is sinusoidal input. Suppose in case of frequency domain analysis, we apply sinusoidal input. This sinusoidal input provides you sinusoidal output at the same frequency. These are all some properties with respect to linear system. When you look at the properties of nonlinear systems, one is stability. Stability is the major point when we deal with the systems. So nonlinear systems may converge or diverge depending upon the initial condition as well as input. So it means so the convergence and divergence will be decided depending on the initial conditions. So you can't say suppose if you say I have an initial condition of x1 equal to 0.5. The system is converging. Suppose the moment you are perturbing with the initial condition, instead of 0.5, you are saying 0.55. The system can go to a diverging point. So this kind of properties, this kind of characteristics will be seen in case of nonlinear models, nonlinear systems. The same thing is applicable for input conditions. So different input or different magnitudes of the input, that system tending to converge or diverge. And second property is sinusoidal input. So when we look at the linear system, sinusoidal input provides sinusoidal output. Here, the sinusoidal input provides non-sinusoidal output. The third important property is when the moment you're talking about nonlinearities, our system with nonlinearity, so basically it introduces limit cycle. What do you mean by limit cycle? The limit cycle basically mean that when you look at this response, so it provides you something kind of oscillation at steady state. Suppose if you say I have a system, I'm giving you a step as an input of the system, right? I'm giving step input, right? So this is the magnitude, my output magnitude. But what will happen is you have a rise time, big time, and overshoot, and etc. Finally, what will happen is it start oscillating at steady state. It is something like this form. So it means there is a fixed magnitude, right, and a fixed frequency. The magnitude of oscillation, that frequency and magnitudes are constant. But it mostly it will not affect the transition behavior of the system. It mostly affects the steady state behavior of the system. So whenever you come across some devices provides you, maybe measurement devices or maybe some control devices provides you some kind of non-linearity. These non-linearities basically introduces oscillations at steady state. So this we call it as limit checking. This is the very basic phenomena, actually, characteristics of any nonlinear system or system. It comes with nonlinearity. But the problem is Laplace Fourier cannot be applied. We apply only linear tools, right? So analysis is also difficult for such a complex behavior system, and but analysis can be done by simulation to find the solution of the nonlinear equations with specific input and initial conditions. As we discussed already, if the moment you are perturbing the input or initial conditions, there is a possibility of going to diverge or become instability. So these are all issues with associated with the nonlinear systems. And the final point I have written here is no universal tool or analytical tool exists to analyze the effect of nonlinearity. So basically, when the moment you talk about linear systems or nonlinear systems, we normally do linearization and we apply control system design and so on. And in case of feedback systems, in case of feedback elements, sensors and other parts, normally we keep we either we introduce the dynamics, which is also linear, or maybe we can use some kind of constant with multiplied with the feedback loop for performing to perform the control system design. But as such, dealing with nonlinear system is much more complex. No analytical tools, much analytical tools available, but you can apply certain tools, but it is not easy. It is complex to do that. But in theory, it says that there are methods for analyzing this kind of systems, comes with nonlinearity or nonlinear systems. So one method which we normally use is a describing function analysis. There are other methods too. Here I have listed out 3 methods here out of 3. The one which is written in the green color, that is describing function method, we are going to analyze it further. The second and third method given is a phase plane analysis, and is basically a graphical tool. And it's basically a 2-dimensional tool, and but the only problem associated with this space plane technique is it can be a graphical method. It's a good method, but problem is you need to reduce the higher order system into second order model, and you have to perform the stability analysis in 2 dimension only. On the other hand, you have Lyapunov stability theory, right? Lyapunov stability theory is one of the best method for analyzing and the design of controllers in the system comes with nonlinearities or inherent nonlinearities. So, but there are advantages, many advantages, many advantages, um, like applicable for both higher order systems, both hard nonlinearities and soft nonlinearities, higher order, second order, higher order systems, and so on. But the limitations which we come across is basically defining the function. Because the system, when you want to define stability in terms of Lyapunov functions and Lyapunov systems, normally we use Lyapunov function, right? Energy function. This finding energy function is basically a hectic task, Herculean task. So in specific, you might have done with x1 square plus x2 square function v equal to something like that, or maybe you might have used some quadratic function, q transpose pq and so on. But there are when you want to design a controller based on using the properties of nonlinearities and so on. So it is not easy. So finding a function itself is a very tough functions, because we worked in adaptive control theory for a long time, and we are using one simple method for adaptive control theory is we normally call as model reference adaptive control method. This approach, actually, if you look at this, we have developed many control system design for Lyapunov systems based on Lyapunov method, but the function to be identified is much more complex. If you study the fundamentals, then you can understand that how complex it is. So these are all problems associated with other methods too. So, but here we are in this presentation, the is concerned, we are focusing more on how the non-linearities are modeled using describing function, then further how it is analyzed, finally how it is predicted, this limit cycle information. This is our whole objective. So let us move on to one by one. And when you look at this figure, the left hand side figure represents restaurant plate dispenser system. So it is what is it basically, it's a mass spring system, right? So if there is no damper, it provides you sustained oscillation. So so some damping should be introduced here. So this restaurant plate dispenser system finally represented in the form of a mechanical system with basic components like the mass, spring, and damper. Okay, this is what we are seeing it here. When you want to write the equation, because normally we write this equation like this. So the force is given here. Normally I write it as F is nothing but M into X double dot plus, and my K times X plus, there is a friction here. So we say friction as constant B. I'm writing it B instead of F suffix B, B times X dot, something like that. This kind of equation, we write it under the assumption that there is no non-linearity created by the spring and dashboard. This is our assumption. Suppose if we say I have some kind of non-linearity in the friction, or I have some kind of non-linearity in the spring, then this whole equation is not valid, because whatever we studied in your control theory and practice is something like this form. So finally we write this is a linear equation. So we write the function with respect to displacement with respect to the force. Maybe in terms of Laplace, we write it as 1 by m s square plus bs plus k. I hope all of you can able to follow it. This is very basic. But when the moment you are talking about a system comes with non-linearity, suppose say for example my spring introduces some kind of non-linearity, because springs are two different types with respect to literature. One is soft spring and second one is hard spring. The type of spring which you are using that introduces some kind of non-linearity. We are not going to discuss it with respect to this equation is concerned, but I'm giving you as an information. And another problem associated, another kind of non-linearity comes from friction. Normally we use this kind of B times X double dot. This is basically with respect to viscous friction, because viscous is the only friction provides you linear response. Because there are other frictions too. You might be knowing that as a mechanical or electrical engineer, we know that stiction friction is the one, right? And second friction is Coulomb friction. These are the two frictions actually introduces non-linearity. Stiction friction means something when you want to move from initial conditions, maybe initial state, normally we need some kind of force. That minimum force to move from the object, maybe that we termed as a friction, stiction friction, and Coulomb friction is basically constant retarding friction. So these are the two frictions basically introduces some kind of non-linearities. So if you include all these things, soft spring introduces some kind of non-linearity, hard spring introduces some kind of non-linearity, then frictions like stiction and etc. introduces further non-linearities. So finally this equation is not valid. F equal to mx double dot plus k times x plus bx dot is not valid definitely when the moment we are talking about all these kind of non-linearity. So what we supposed to do? We supposed to include all these non-linearity into account there, or we need to model it and we need to include it properly so that you can able to validate the model whatever you obtained analytically with experimental systems. Okay. You have the basic equation for what we write here only by under the assumption that only friction is introduced. Friction provides some kind of nonlinearity, and spring is not providing any kind of nonlinearity. Under this assumption, Van der Pol equation, differential equation, written as m y double dot plus b times y square minus 1 y dot plus k times y equal to 0. So if you look at here, this here the friction is introducing nonlinearity. So instead of b times y dot, like I have written it like b times x dot, right? This is b times y dot. This so here is b, and instead of x, I have written y dot here. So this is the component, the whole component introduces y square minus 1. That introduces nonlinearity because of frictions. So assume this equation is equation, and where m, b, and k are greater than 0. So what will happen here? As we clearly understood that b times y square minus 1 times y double dot, that actually this component, the second component, friction component, introduces some kind of nonlinear characteristics. So these characteristics, how it introduces limit cycle or oscillations in the output side. So when you look at the values with respect to the y is the output, right? So for large value of y, what will happen? The system motion actually tending to converge, because that coefficient become positive. And the moment you're talking about a small value of y, so the whole component become negative, right? So the system starts diverging. So this is happening simultaneously. In turn, you see that the damping varies with y, and the system motion can either go to either can grow or unboundly or decaying to zero. So this actually provides you the sustained oscillations. So this sustained oscillation is independent of initial conditions. So the thing is, the sustained oscillation is independent of any. So the small changes will change that. Will not change any kind of magnitude change in the oscillations. Okay, this is actually to just to make you to understand the limit cycle from the van der Pol equations. When you look at linear process, linear systems, normally what we see actually is linear systems. Normally we write in the form of transfer function, or maybe we write in the form of state space, x dot equal x plus bu and y equal cx plus du, right? In case of transfer function approach, normally what we see here, we plot the poles and zeros in the S-plane. So this is my sigma and this is my j omega plane, and we used to plot the poles, and this left hand side normally we say that stable region, and my right hand side we used to say that is unstable region. Unstable region, right? Suppose when the linear system provides you or introduces sustained oscillations when the poles are lying on the imaginary axis, right? When you look at the poles, suppose if the poles are lying on the imaginary axis, suppose if I have poles something like this kind of poles normally introduces sustained oscillations. So this is my step input, and so what will happen now? Your system starts oscillating. It start oscillating. So it means in case of linear system, you can able to see, visualize the or you can produce the sustained oscillation only if the poles are lying on the imaginary axis. All right, and the amplitude is determined by its initial condition. Basically, such systems are very sensitive to the system parameter variations. In the sense, suppose if there is a small disturbance into that particular system, either the pole can move to right hand side of this plane, become unstable, or can move to left hand side of this plane, become a maybe stable processor. So instability or convergence will be decided based on the parameter variation, and the parameter variations are too large and mostly it is tending to diverge, and is too small, maybe it may be lying on the imaginary axis, or sometimes it can move to the left hand side of the plane, depending on with respect to the normal parameter condition. But in case of nonlinear system, this limit cycle magnitude is independent of initial condition. As we told, it is never depending on the initial conditions, and in the limit cycle is not easily affected by the system parameters. Even there is a parameter variations that will not give any effect on the system response. Okay. The linear system with the periodic input may exhibit a periodic output whose frequency is either subharmonics or harmonic frequencies. The moment you talk about any sensor or maybe a controller part or maybe a system introduces some kind of nonlinearity, that actually introduces some kind of higher order harmonics into the loop. So only with instead of going with the fundamental harmonics, because most of the control system design works with fundamental harmonics. The moment you talk about the higher order harmonics due to these non-linearities, either in the sensor side or maybe in the plant side, so that actually provides you, introduces harmonics in the system response. Okay, so last one, this we talk about the jump resonance. So this is another property actually of the nonlinear systems. Suppose when you draw the plot, when you draw the frequency plot here, right? This plot actually shows that frequency in x-axis and magnitude in y-axis. Magnitude versus frequency plot. That is Bode magnitude plot actually. So when you're doing with we are doing with the loading characteristics of frequency, so it goes like this. Like you see that it starts from here and it moves like this and reaches V1, and actual point is supposed to be the dotted path, and finally it has to reach this place. This is the original magnitude response supposed to be there. But because of this non-linearities, what will happen is it goes to the B1 and then it directly jumps from here to here and reaches here. It goes like this way. So instead of taking the path of B1, B2 and things like that, it simply jumps from B1 to here and it reaches this point. Maybe I would like to say this point is A1. Okay. So when we are unloading characteristics, frequency characteristics, what will happen is it goes like this way, and It goes like this. It goes like this way, right? It will not take the path from P2 to B1. It simply jumps from B1 to A1, and it reaches its final path. So this kind of response behavior, we call it as resonant jump actually. So this is it's very common actually in case of aircraft systems, radar systems in aircraft, and sailing systems, ship sailing systems. You might have seen that a flight, when you want to have a direction change, or maybe something, there's a wing, the rudder behind. It will change its position. So you can see the sound actually, something like a tuck sounds. So these sounds, these actually this kind of systems, I would like to say, introduces such a kind of behavior or phenomenon, resonant jumps. So this is very dangerous actually, and we need to have a control systems such that your system should be stable always. Okay, let us talk with describing function, because when you want to do analysis, when you want to do certain analysis or understanding the characteristics of the nonlinear systems, we need to have a model like a physical system, like mass spring systems. We can write in the form of differential equation, or can be written in the form of state space equations based on the differential equation. So, or maybe even differential equations also can be written. So, but when you want to talk about any nonlinearity, so such models are needed. So here we are trying to understand how these models can be developed. Okay, this is what the first objective is. So we are trying to see now and how that nonlinearities can be modeled. So we termed as a describing function. So like our transfer function in S plane, this is a describing function in and for analyzing the nonlinear system or nonlinearity. Okay. So what are the assumptions normally we make? So as I told in the previous slide, there are two type of nonlinearities. So one is soft nonlinearity, and second one is hard nonlinearities. So soft nonlinearities can be written in the form of equation itself, like dy by dt the whole square, and sine cos, etc. So on this kind of mapping equation. So it's basically a soft nonlinearity we termed as. So equation itself comes like that. But this is soft nonlinearity because mathematically we can represent those nonlinear systems. But in case of hard nonlinearities, we have something like a saturation. Say for example, in case of amplifier, or in case of converters, A to D converter, or D to DC converter, whatever. So these kind of systems actually basically introduces some kind of nonlinearities like a saturation, maybe plus or minus VCC, beyond which there is no output, right? Your signal gets saturated in case of amplifier. In case of ADC, A to D converter, depending on the resolution we select, right? The type of and the type of conversions. So we used to have 5-bit conversions. I used to have 6-bit conversions, 11-bit conversions, 16-bit conversions, so on. Depending on the usage, depending on the requirement, normally we decide what kind of conversions required. So that quantization error also occurred, right? This is basically a dead band. It introduces dead band. All of you are aware that we call it dead band because there is no input. There is no, for small certain incremental input, there is no output found there. So we call this dead bands. So something like that, like a backlash we are talking about. In case of mechanical transformer, like a speed control systems, when you want to reduce the speed of the motor, or when you want to increase the speed of the motor, normally what we do, because the motor will run at a high, run with speed, some speed, and we used to have a gears, right? Constant motors run at constant speed, and we used to have gears either to step up or step down, like a transformer. So we call this mechanical transformer. That is nothing but gears. So these gears basically introduces some kind of nonlinearity like a backlash. So like that we have many non-linearities which are available actually either in the measurement side or in the plant side. So even sometimes in the control side also. Okay. So these are the non-linearities. These kind of non-linearities we basically call it as hard non-linearities, and it is separable. What do you mean by separable? You can write the equation and it can be separated. So in the sense, suppose if you have a system, I can separate the system something like a linear part and non-linear part. So linear part I can represent it in the form of a transfer function. Say for example, in case of water control systems, water I can write it as a transfer function, something like 1 by. Suppose if we say I have a motor system, something like this, something like a motor. So I have a transfer function of the system, right? So my transfer function is here, and discrete function is here. This is motor comes with this. So motor model is here, and this is my gear model. Okay. So motor model, maybe I would like to say something like a second order dynamics as 1 by s times s plus 1, and I have a described function method. I normally write it as n of x. So this is my g of x. Transfer function of the motor is g of x, and gear is my, say, for example, n of x. So this kind of classification, or this kind of separation should be seen first in the plant. Only with this idea we can apply and we can do the analysis further. Suppose if these two are not separable, then this method cannot be applied. So you need to apply only with either Lyapunov function, or maybe you can go with the phase plane methods and or other methods, delta method and so on. So this method is applicable only, but why we are stressing this method? You might be, you might be raising the question, because this is one of the best method and simplest method to study and analyze the nonlinearity compared to other methods. That is the beauty of this. So the separation is required. If something you can able to see visually with your eyes, and you can able to do this analysis. So linear part can be separated, non-linear part can be separated from the linear part. So linear part basically we represent the form of transfer function or state space, and non-linear part can be represented the form of describing function. So like other methods, because nonlinear, the hard nonlinearities, and we know that the separable nonlinearities. This is also be understood, but nonlinearities cannot be handled as such. So what we are doing here, we are trying to approximate the nonlinearity, like what you are seeing in the previous studies. Nonlinear equations will be given, and we are linearizing the equation with the help of Taylor series approximations. Like that, we are also doing here. We start with it. Normally we do with a linearization approach. So it means we are assuming that the system is actually that the nonlinearity is represented only with or approximated only with the fundamental harmonics. So that's why we call it as harmonic linearization. So this normal harmonic linearization is termed because we are approximating this nonlinear equation, nonlinearity into a linearized model. So we call it as harmonic linearization. But this is under the assumption that, because this is under assumption that the system, your closed loop system, provides a good low pass filtering effect. Like I told you, this nonlinearity can occur in the feedback side or feed forward side. Feed forward side means plant side, feedback side means sensor side. So, but normally we are assuming that whatever the controller we design and with the systems work with a good low pass filtering effect. It means all higher order harmonics will be attenuated. That is the basic idea behind the design. But suppose if that system is providing a poor low pass filtering effect, so what will happen now? Your higher order harmonics also will sustain. So in turn, based on this method, if you do some analysis, that leads to some kind of error, or it can mislead also some with respect to control system design. So that also should be careful. So we have to ensure that the system provides you low pass filtering effect. So we come across with this how to overcome, but still we are finding difficulty in overcoming 100%. I can explain you that at the end of this presentation. Okay, so it predicts this method. Finally, describing function along with the plant characteristics predicts the existence of limit cycle. So what is mean by limit cycle? It says oscillations, right? At steady state. So constant magnitude and frequency at steady state. That oscillations and frequency, the magnitude of the oscillation and frequency will be determined or observed based on this described function method. This is our whole objective of this presentation today. So basically, finally, we call it as is basically Fourier series approximations, right? Any systems can be approximated into any nonlinearities can be approximated into the harmonic linearization with the help of a Fourier series method. Okay, let us understand first Fourier series. So we all are aware actually, because we studied the mathematics of Fourier series and Laplace transform and Z transform. These three transformations we studied actually in our theory, basic theory in engineering and science. So we know that y of t equal to y of t plus t, and y of t we normally write it as a0 by 2 plus sum of a n cos n omega t plus b n sin omega t. And an and bn are defined as the integration of 2 by 2 integral y cos t omega t, and the b is with respect to sin t omega t. So with respect to different signal, right? So this also, that parameter also can be varied. Like in case of even symmetry, if you are dealing with a signal, even symmetry signal, your y of t becomes y of minus t, that bn equals 0, and there is no sign term. when you are talking about odd symmetry, so there is no cost term, that is a n equal to 0, and your equation y become minus y times minus t. And you have odd half asymmetry also. We can see the examples maybe in the next slide. If you look at this slide, this I had given you a sinusoidal response in the first case, and it is basically a Fourier series of a square signal. So what do you mean by here? I have a first signal is sinusoidal signal here, and there is no secondary signal here, so the same signal is reproduced. And in case of spectrum, if you look at the spectrum, I can able to see that spectrum of the frequency, right, is only one frequency, one signal. This magnitude and frequency is visible here, right? When you are adding a third harmonics, so this is my fundamental harmonics, and I'm adding a third harmonics. The red line represents your third harmonics. What will happen now? It becomes a non-sinusoidal response. So the composite waveform is shown here, and the spectrum is clearly visible actually. So first order fundamental harmonics with the magnitude is given, and third order harmonics with the magnitude is also represented here. And when you look at the when you are introducing a fifth order harmonics, so 1, 3, 2, and 3, 5, and finally they become more sinusoidal, more non-sinusoidal response. So what is happening here now? Here, by adding one by one, right? Finally, it becomes a square wave. So this is what you can able to see here, the response. So by adding a more signal, more fundamental signal, 1 plus 3 plus 5 plus n, etc. By adding the signal, right, harmonic for 1 to this, so I can able to make that I can produce a square signal. This is what you are seeing in the graphs. Okay. So what the signals what we are talking about, that even symmetry, odd symmetry, and odd wave symmetry, these are some examples which I have shown here. The triangle pulse is shown here, there is even symmetry signal, and the second one square waveform is given as a pulsed kind of waveform. We call it as odd symmetry, and the last one we termed as an odd half wave symmetry. So depending on the signal, that the parameters as we discussed in the Fourier series will vanish, and we can able to find the output equation y with the a cos omega t and b sin omega t. Okay, but most of the time in measurement and controls, measurement and control side, mostly odd symmetry and odd symmetry will be appearing, and even symmetry rarely is not appearing so far. In my experience, there's no even symmetry I got found so far. So only odd symmetries and odd asymmetries are there with respect to measurements and control system design. Some of the non-linearities in control system design in basic engineering, like I told you, saturation is one, and then friction is another. This is a very important phenomena. It's like an on-off switch, on-off kind of switch. I told you the stiction friction is something like this form. Say stiction friction is only at this point. Only at the starting point we have this. This constant retardating friction is actually Coulomb friction. So stiction is here, and this is Coulomb friction is here. Without this point, only Coulomb friction is there. Coulomb friction maybe something like on-off switch kind of. And dead zones, like we told, most of the converters designs mostly it introduces ADC and etc. It introduces dead band. So this dead band also create limit cycle oscillations. Our system experiences with limit cycle. And we also discussed about this gears, right? Mechanical gears. This introduces a kind of backlash. This is what is shown here. Okay. So your classification is something like what you see in the upper side, some saturation, friction, and dead zone, and etc. And you are also seeing a kind of a backlash in the mechanical system. You can also see something like a hysteresis, right? The hysteresis response in the magnetic materials normally produces hysteresis behavior. So we normally compute hysteresis loss, current and hysteresis loss, and so on. So that also kind of loop. This is similar kind of loop actually. This kind of loops actually introduces limit cycle behavior in the output side. But these are all we simply ignore actually during the time of our design and process. But it should be taken into consideration at least after listening this this presentation. We'll see that how that describing function is presented. So let us look at the diagram now. The diagram shows G1, G2, and N of X. So we'd like to define what is G1, what is G2, and what is N of X. Like we said, any feedback system, it comes with a plant, right? Normally we write plant controller. So this could be your plant. Normally we write as G of S. So I'm writing this G2 of S here. Okay, representation will be different, but whatever, you can write any kind of representation. And controller we write C of S, but here I'm writing a GC of S. We normally write GC of S. Here I'm writing this G1 of S. This is my controller. So I have a plant. This is my plant here, and this is my controller. And the system comes with some kind of nonlinear. Assume the nonlinearity is a saturation is the nonlinearity, right? So the saturation should be fit into here. The model of the saturation should come here. That this is what the meaning is. So I have considering either I can consider either input nonlinearity or output nonlinearity depending on the system which we are dealing with. Suppose if you are dealing with a motor with a motor control system, right? Motor control system comes with a transfer function G first, then if it comes with a gear, it will be added to the next. So your G to come first and N of X will be next, because it is in the next it is in the it is in the second level. So normally we call it as output nonlinearity. So nonlinearity can be in any place. Input nonlinearity, sometimes we can call it as we can place it in the output nonlinearity, or sometimes the nonlinearity can be in the feedback path as well. So it is actually all these things are basically with respect to the systems which you are dealing with. So depending on the condition, depending on the way which you are separating the nonlinear from the linear models, that you have to place it accordingly. So here I'm assuming, right? I'm assuming that feed forward nonlinearity is considered and input nonlinearity is there, actually system with input nonlinearity. So what we are seeing here, I'm looking at only the focusing on this x equal to y, right? X is the input and y is the output, and nonlinearity is we describing function, we call it as n of x. That is a model like g of s. So what is x here? And as we discussed in the previous slide, the system, closed loop system, should provide a low pass filtering effect. Low pass filtering. It means always you get the sinusoidal output. That's what we are saying, that your x should be a sinusoidal. So my x equal to capital X sin omega t. But when the moment we are giving this as an input, the nonlinearity, your output is definitely non-sinusoidal. This is non-sinusoidal. So it means you have y equal to y naught plus a1 cos omega t, b1 sin omega t. It goes like this. So this is basically written from the Fourier series, as we already discussed in the previous, or we know that already. So, but what we are doing now, so this y of n is, since we are dealing with the odd symmetry and the odd half asymmetry, there is no y of n here. This is 0 here, and only these components will be, the cos and sine components will be there with respect to different magnitudes. But since we said that we are going to have a system with a good low pass filtering effect, so we are eliminating all higher order harmonics. So it means what will happen now, finally I'm writing this equation as y equal to a1 cos omega t plus b1 sin omega t, right? So so it means we are considering only fundamental component. So all higher order component from second to infinite component, we are removing, actually only we are considering a fundamental component. Means your equation y become a1 cos omega t plus b1 sin omega t. This is what I have represented here, y equal to a1 cos omega t plus b1 sin omega t. This is under the assumption that we are closed loop system. This system would provide very good low pass filtering effect. Suppose if we fail to provide low pass filtering effect, definitely this signal, this x will be contaminated. This will be contaminated, mixed with the higher order frequency, high frequency signal. Hence, the whole analysis will resulting maybe a signal or different signal, which may not be favored to us. Okay. So what is a1 now? 1 by pi 0 to 2 pi y cos omega t, b1 equal to 1 by pi integral 0 to 2 pi y sin t omega t. This is all the definitions. So I need to find from this what is a1, what is b1. Simple, that's all. So this is that's why we call it as harmonic linearization, because this describing function method is applied only with respect to the fundamental harmonics. Suppose if you are considering all higher order harmonics, yes, you can able to measure, you get the better describing function, maybe with more accuracy. We are dealing first, we are starting to understand the behavior, characteristics behavior or design control designs. Normally we start with the only fundamental harmonics. Okay, so what is n of x? N of x is nothing but describing function, right? This describing function is basically input is x, capital X is the input, because depending on the input, like we said, the input is x here, this capital X here. So this, depending on the input, it changes, right? So the function will vary. So also frequency. So depending on the input and frequency, this characteristics n of x can vary. Okay. So, but the major problem associated with this describing function is here.
मी सोमवारी प्रेझेंटेशन देतो मॅडम, रेडी करतो सर कोणी
Okay. So here we talk. Yeah. when we talk about describing function here, it predicts the existence and characteristics of limit cycle. This is what our objective is. But we can able to do that. Our objective definitely will match. But what is the problem associated with this kind of analysis? The major problem is false identification cannot be ruled out. This is the biggest problem, and which we observed actually when during the time of our simulation studies. And I would like to showcase you where the false identification comes and how this false identification can be eliminated or maybe can be corrected, I would like to say. So that is why we need to check with the what simulation system comes system with the nonlinear simulation itself. So nonlinear simulation also equally important actually to just for validating the method which we are proposing, which is available in the literature. That is a describing function method. Okay, this is very important. Let us understand first the topic of describing function for nonlinearities. How it is done first. Let us take a very simple example, like a simple friction. That is a friction we defined as an on-off relay. So I have a system here, as we discussed in the previous slide. Small x is nothing but x sin omega. I will go back. This is my x here, and this small x is nothing but capital X sin omega t. We are assuming that the system provides low pass filtering effect. Under this condition, my input to the nonlinearity is capital X sin omega t. So I have drawn a sinusoidal response, right? With the capital X is the magnitude, with the frequency omega. So what is my nonlinearity? I am considering a nonlinearity as a relay, simple relay as a nonlinearity. So you assume that your system provides, your motoring system provides your Coulomb friction. So it is normally provided in the feedback path actually in the motor when you are writing the transfer function of the system, or maybe making the block diagram of the DC motor system. This friction will be coming in the feedback path. So it gives you some kind of friction, that is Coulomb friction. In constant returning, it always oppose actually the friction, oppose the force or torque introduced by the design, this motor. So this is our nonlinearity here. And what will be the output actually? We clearly know that only at 0, this is 0, right? When it's 0, if you look at this 0, it is m. Sorry, it is m. And further varying values, so further change the values, it is constant. So when during the time of cycle, positive cycle, so you have a response at this point, right? It's like a pulse, something like this. And during the negative half cycle, you will get a negative response. It goes like this. So it is basically introduces or provides or generates a quiet signal, right? It's very simple. So pulses, you have a nonlinearity, on-off relay is a nonlinearity. In physically, we say that friction is the nonlinearity, Coulomb friction, and I'm giving input as sinusoidal. And what I expected was the square waveform. So square waveform is a time term. So what is the magnitude? It toggles, because basically this on-off switch basically toggles between plus or minus m, right? So this was plus, and this is the magnitude of plus here, plus m to minus m, it toggles, and it's basically a square waveform. So you have to have first step this. So when you want to have a differential describing function model, the first step is nonlinearity is available. You apply the sinusoidal signal x sin omega t and get the output non-sinusoidal signal. Here, the non-sinusoidal signal is nothing but square waveform here, right? That is what we obtained here. So the output signal y of t equal to m. So this is nothing but m when the omega t is varying between 0 to pi. And pi to 2 pi, it is minus m. It is switching actually between plus m to minus m. So this is what we have seen. I am writing the mathematical form of this signal. M when omega t is varying between 0 to pi, and minus m when omega t is between pi to 2 pi. So what is your Fourier series? Fourier series are already defined. Y of t is nothing but a naught by 2 and sum of a in cos omega t plus b in sin omega t. So since we are talking about this is odd symmetry signal, a n equal to 0 and b a naught equal to 0. So this components will not be there, and your a n also will not be there. Cos component will also be 0. So only component is nothing but y is nothing but b sin omega t. Suppose if n is nothing but 1, 2, 3, 4, and x, all higher order harmonics also included, but this derivation is made only with the fundamental harmonics. So we normally write psi b1 sin omega t. So my y output equation y is supposed to be b1 sin omega t, right? So we need to find what is my b1. That is what our second objective is now. So y equation is written from this Fourier series, y equal to b1 sin omega t, because we are considering only with the fundamental harmonics. Now we need to understand, we need to find what is b1, and then only I can able to find my y. So now I had given a step-by-step procedure how to find the value of b1 or b. So b is nothing but 2 pi t 0 to t y sin n omega t d omega t. That is 2 pi, right? One full cycle is considered for this computation. So bn is nothing but 2 pi 2 pi 0 to 2 pi y sin omega t d omega t. It is written here, and by replacing t with 2 pi, and we can split into two components. That is because your signal, your output signal, that is square waveform, is toggle between plus m to minus m. So one is with respect to m plus m, and second one is with respect to minus m. So I am splitting into two components. One is 0 to pi, this is plus m, and pi to 2 pi, and the magnitude is minus m. So the remaining things are constant, m sin omega t and m sin omega t and minus m sin omega t d omega t. So take the integration, and finally you get the solve the equation. You get m by n pi minus 2 times cos n pi plus 2, where n equal to 1. So m by pi minus 2 cos pi plus 2. So cos pi is minus 1. So it become minus become plus. So what will happen now? This is going to become 4m by pi. So this is what my b1. This is nothing but b1. So like I told you in the previous slide, y equal to b1 sin omega t. So b1 is obtained. So from the general expression is bn, and because we have specific expression is only b1. So under the assumption that higher order harmonics are eliminated. So now my y equal to 4m by, so I have written here itself, b1 sin omega t. So 4m by pi times sin omega t here. And what is your describing function now? So describing function is defined like output to input, right? Output is y is the output here, and what is your input? Input is x is the input. So like we are going to previous slide, output is, this is my input and this is my output. So my output is y is nothing but y1 here. So it becomes y1 by x. So this y by x. Suppose if you write the expression y2 small x, that is capital X sin omega t. So you have sin omega t cancelled. So what is your resultant become? Your resultant become 4 by pi x. So this is the describing function. This is the model, right? That is nothing but describing function for the nonlinearity. What is the nonlinearity we selected? Simple on-off switch. Simple on-off relay is considered for that. So this is the first point. So like that, we can derive the expression for many. So this is available in most of the textbooks, control system engineering textbooks. So you can use, for example, suppose I'm introducing a dead band. So instead of going with relay, I'm introducing relay with the dead band. So it means instead of only switch off on off, the dead band is introduced. This is my dead band. Delta is the dead band, plus or minus delta in x-axis. So what will happen now? Because of this delta, there is no output till the point alpha. Only after alpha it switches, right? So it toggles with m. So it means only the duration alpha to pi minus alpha, the magnitude m exists, and other values like this before and after, maybe that alpha to pi plus alpha magnitude will be 0. When it become minus m, that the interval of omega t becomes pi plus alpha to 2 pi minus alpha. So this response repeats. So we are considering from 0 to pi, 2 pi. So if you look at this 0, this is the first case, and m, when it is toggle only with when it starts with the after dead time. So that is alpha to pi minus alpha, and 0 again, then minus m, then 0. So we need to consider only these two ranges, right? Alpha to pi minus alpha is 1, because only that point the magnitude is m, and second one is pi plus alpha to 2 pi minus alpha, the magnitude of the response, output response, is minus m. So this, after finding this, because this is a 3-step method actually. One is this, we need to find the equivalent response, output response. From the output response, you need to write the signal in the form of mathematical expression. Once it is done, you can apply the Fourier series expression. So this is also a symmetrical waveform. So we are keeping a1, an, and an at 0. So it comes with y equal to b sin omega t. Same procedure you apply. So I am applying with the same procedure for finding this b. B is nothing but 2 by 2 pi, and 0 to 2 pi y sin omega t d omega t. So that interval exists only with the 2 points here. That is alpha to pi minus alpha and pi plus alpha to 2 pi minus alpha. Remaining, the magnitude is 0. So this only we are writing with the magnitude alpha with respect to the interval alpha to pi minus alpha. Pi plus alpha to 2 pi minus alpha, the magnitude is minus. So just take the integration and you get the final expression. So we got the final expression as this here, 4m by pi cos alpha times sin omega t. So this is my output y. What is my response x? So x is nothing but small x is nothing but capital X sin omega t. So I can write the final expression like output y2, y here I have written as y1 because with respect to fundamental harmonics. So y equal to y2, we say that x. So x is nothing but x sin omega t. The sin omega t will be cancelled. So the remaining will be 4m by pi times cos. So alpha can be cos alpha. Sorry, this is cos here. Your cos alpha can be obtained as your cos alpha is nothing but square root of 1 minus del square by x square. All these informations are known as the delta is known to you. It should be measurable first of all because separable nonlinearity and the nonlinearity bands also should be measurable or available. So delta is known to us and x is the running parameter here. And so based on this, you can able to find what is your cos alpha. Through this, I can able to find every value of x. So n of x is again a plot. So it means x can vary from 0 to infinity. Okay, x can vary from 0 to infinity. Okay, so this is the second example, and I would like to show the third example is case 3 is backlash. Okay. Okay. So the third example is a backlash. Like we said, the mechanical transformations, mechanical transformers, like a gears, basically introduces some kind of backlash, non-linearity, which is nothing but a backlash. And if you see this, I'm applying the same sinusoidal response here, and got the trapezoidal response as output because it starts with here. Because when the x is 0, right, it starts with some y. So y starts with minus h, and when it gradually increases, linearly increases till the point of pi by 2, and it is steady at steady state at capital X minus h till the the omega t is pi minus beta. Then it starts decreasing. It's going in the negative direction, and till 3 pi by 2, and it goes constant till the 2 pi minus alpha. Then it starts linearly increasing, and the response repeats. Okay, further increasing the omega t. So we have to write the equations accordingly. X minus h when the value of omega t is varying between 0 to pi by 2. Like that, we are written the expression like previously. All right. So this equation should be written. So first step is you have to draw the plot. This plot is needed, and then from the plot you write the equation. This is your second step. And third step, you apply into the Fourier series expansion. So Fourier series expansion, this is basically odd Fourier symmetry, and only there is no a0 component. So you have component both cos and sine component. So your y becomes, instead of b1 sin omega t, we have a1 cos omega t and b1 sin omega t. Other higher order components are eliminated. So a1 is here, b1 is here, and this is a little lengthy expressions. It takes some time to solve the expressions. I have given step-by-step procedure. Once the presentation is over, maybe you can go through and you can get these details steps. Even the solutions are available in most of the textbooks, conventional textbooks, control system textbooks, which deals with nonlinearity. So this is a1 2 pi by, and with intervals 0 to pi. Then second interval is this, and third interval is this. So we are limiting it to pi because to limit the complexity, I limited 0 to pi since the signal is repeating actually after pi by 2, after pi. So we stopped with this, and you find the magnitude a1. So we have computed the magnitude finally as this. This is the magnitude of a1. Like that, we can find the magnitude of b1. So b1 also we found the magnitude of b1 is this. Using the same integration only, so there is no much problem associated with it. But only thing is it takes some time actually to derive the expressions. So you go step by step and do this, and you get the final transfer function, final value b1 as this. So after that, you need to combine, right? b1 plus ja1 by x. So after combining this equation, you get the final describing function as this. So what is the difference actually which we are seeing actually from the previous nonlinearities and this nonlinearity is, if you look at the first nonlinearity, 4m by pi x. If you look at the second nonlinearity, 4m by pi x times cos alpha. So till this point, there is no complex terms available, right? Enter into that. But when the moment you are talking about backlash kind of non-linearity, it comes with finally it comes with a J component. It will be represented that non-linearity itself represents the form of complex variable form or complex form. Okay, so this is the only difference. So that based on this classify these things, we are classifying the non-linearity into two types. One is memory non-linearity, and second is non-memory non-linearity. So these memory non-linearities are, there is no histories required. So like memory, like our saturation, like our relay, first case of relay, switch, whatever we say, the relay or switch or relay with dead band. These non-linearities, there is no previous histories required. So this kind of non-linearity we could term as memory non-linearities. This memory non-linearities, sorry, non-memory non-linearities, I would like to say this, non-memory non-linearities. This non-memory non-linearities, there is no previous histories needed. Okay, so when you look at the describing function, differential equation, that the describing function form, we always see one numerical value, number, 4m by pi x or 4m by pi x times cos alpha and so on. So this kind of non-linearities provides without any J component, complex variable. But when the moment you are dealing with a non-memory component, like I told you, the backlash is one which we are seeing, or we can see that hysteresis and so on. This is actually from a loop, and whenever you want to compute the loop, actually previous data is always required actually. Okay, to complete the loop, you need to have previous data. So some kind of history is needed. So this kind of non-linearity called as memory non-linearity. The backlash and etc. are under this memory non-linearities. So these non-linearities basically provides you the component J component, that is complex variable component. Like we would like to recap before moving on to the second topic of this analysis. We would like to see what we had seen actually. So we had seen odd symmetry non-linearity, that is saturation on off and on off with dead zone and so on. So these are all without any memory. There is no memory in it. So these are all non-memory non-linearities, we call it as. And order of symmetries non-linearity we dealt with. That is, we also study the discrete function. This discrete function contains both real and imaginary part. So one example we had taken was backlash. I like that other examples too available actually in these systems. But the event symmetry we are not dealing with it because event symmetry is not occurring actually, not available occurring in the control system loop actually with respect to measurement systems. So I have not seen, but mathematically they derived and they have that analysis and so on. But practically, I have not seen this event symmetry non-linearity occurring in the engineering loops, actually, control system loops. So I have not dealt with that. But when you want to develop for a discrete function for such systems, that provides only imaginary term. Like I told, non-memory non-linearities provides a real term, and memory non-linearities basically provides both real and imaginary term. When you want to deal with even symmetrical non-linearities, that actually even symmetry means like a triangle waveforms, what I have shown like as an example. This provides you only imaginary term. There is no real part available actually. Okay, but this kind of non-linearity we have not seen. But if someone come across, I can let me know so that we can see that. But analysis and analytical methods and analysis are available for event symmetry as well. But we are not dealing with this. We are dealing only with odd symmetry and order of symmetry. Okay. Let us move on to the stability analysis now. So, and when you look at the linear system, right? So we studied in control system, maybe in even measurements or advanced measurement systems. We always studied that stability using Nyquist stability criteria. There are many methods we use, like a root locus technique, maybe you can use Nyquist plot method or Bode plot and so on. So there are many methods, even inequal charts and so on. There are many methods we use actually to check the stability of the system. So here we are dealing with a Nyquist plot. So because this is the one method which is used for predicting the frequency, limit cycle frequency or limit cycle information. Actually. So so I want to give some kind of introduction before moving on to how this Nyquist plot can be useful for predicting the limit cycle information or checking and finding the limit cycle information. If you look at this, it's a loop consists of a feed forward path k times g of s, and the feedback path is h of s. So k times g of is the planned transfer function with maybe controller allow controller, and h of s is the feedback elements, which now basically comes with the sensor components, sensor along with the signal conditioning component. Transfer function is nothing but h of s. So we normally keep h of s is equal to 1, that is unity feedback systems, but practically we have h of s too. Sometimes actuator will be in the feedback. Sometimes some sensor like a temperature sensors, maybe it provides your first order dynamics, or sometimes second order dynamics, and so on. So depending on the sensors, normally we need to include the HFS transfer function also. Okay, but practically when you want to design a controller, all these things should be taken into consideration. If you are assuming to be 1 here, definitely the control system will not work, or maybe it will introduce a bad response, or maybe an unwanted response for during the time of implementation. Okay, so what we are going to do here, actually, what we are seeing actually here is, normally we cover the entire right hand of the plane, right? So because we always look at the any poles are lying on the left hand side, right hand side of the plane or not, because if the poles are left hand side, no one worried actually, because it's stable. But here we are talking about the systems whose poles are lying on the right hand side of this plane. So this is basically comes from the conformal mapping theorem, and we are not going to discuss in detail here. Just I'm going to give only essence of the Nyquist one here. So what we are saying is he's trying to map the entire right hand side of the S-plane to the mapping into the other plane here, real and imaginary plane. So what is happening now here? So suppose if there is a pole, so this is actually a k times GFS HFS plot, right? Poles, position of the poles, and he's covering the complete entire right hand side and checking that any poles are sitting in the right hand side of the S-plane or not. So number of open loop poles sitting in the S-plane, suppose if it provides you number of encirclement with respect to -1,0, suppose -1,0, because -1,0 is the critical point, because it is from the magnitude plot is -1,0, right? So this is my k times GFS by 1 plus GFS HFS equal to 0. So my k times GFS, my characteristic equation become 1 plus GFS HFS equal to 0, k times. So k times GFS HFS equal to -1. So the magnitude from the magnitude plot, we always get 1 plus or minus j0, right? So this is what our critical point is. So when something is encircling a critical point, now basically the system, from the whatever we can understand that closed loop system is unstable. Something which is within the limit -1,0, the system is basically stable, right? Suppose here what we are seeing is, here is a mapping. Suppose normally if you map the systems, basically it maps to the origin, right? How many times it ends. This is what we got seen in the conformal mapping. But since that critical point is shifted here, so we are always looking at the how many number of encirclements present. Suppose here, if you assume to be here -1,0, assume instead of that I'm shifting it here inside. So there is a one cycle, right? This is one cycle. So suppose assume there is a pole which is sitting in the right hand side, open loop pole which is sitting in the right hand side of the S-plane. Okay, open loop pole which is sitting in the right. When you are talking about the closed loop stability, we are looking at the number of encirclements with respect to -1,0. Suppose if there are one encirclement and one pole with one encirclement, that tells you that the closed loop system is stable. If not, the system is unstable. This is what the theory says. Nyquist stability theory says. I had given some explanation at this place. You can go through it. Okay, now actually this is all done. We have done actually control system design only with linear models. Suppose the moment you are talking about non-linearities or non-linear systems. So when you talk about non-linearities here, n of x is also available here. So what will happen now? My transfer function, suppose if we say my output is y and the input is r. So I would like to say y to r is nothing but n of x times g of s divided by 1 plus n of x times g of s. So previously there is no n of x. Now because of the non-linearity, input non-linearity can be input non-linearity, or maybe it can be output non-linearity, or it can be feedback non-linearity. So we have a transfer function which is nothing but n of x. Since it is a fundamental with respect to approximated with respect to fundamental harmonics, it is very well we can write the transfer function of the system with n of x. So n of x g of s 1 plus g of s. So what will be the characteristic equation? My characteristic equation will be this: 1 plus n of x g of s equal to 0. S equal to j omega. I have replaced with s equal to j omega here, so it is written here. Okay, now what is happening now because of this? Previously 1 plus g of s equal to 0, g of s equal to -1. So my critical point is -1, 0. No non-linearity. If there is no non-linearity, my g of s equal to -1, g of j omega equal to -1. That is -1, 0, -1, j0. So my critical point is very clear there. But here what will happen now? Here 1 plus g n of x also would be entering into the zone. So what will happen now? My g of j omega is nothing but minus 1 by n of x. This is the difference now. Previously minus 1, if there is no nonlinearity, my g of j omega equal to minus 1. If there is no nonlinearity. But the moment you are including a nonlinearity, maybe it can be a feedback, feed forward, or feedback, or whatever. So here we are reducing input nonlinearity here, n of x, input the plant. That's what meaning. So 1 plus n of x equal to n of g of s equal to 0, and g of j omega equal to minus 1 by n of x. Right. So what is happening now? There are two locus now. Previously we have only one locus. Normally we draw the locus like this, right? So g of j omega. This is a real part and imaginary part. And g of j omega is done, and omega is the running parameter, varying from 0 to infinity. But this case is different here. This case is different because of two functions. One is this function. This function can vary from omega equal to 0 to infinity. And you have another function the right hand side, minus 1 by n of x, where x is varying from 0 to infinity. So it means you can able to see that there are two locus. So and it cuts at some point, because since it is equal, right? It cuts at some point. So meeting point. So I'm saying you need to plot this first. This is the first point varying from 0 to infinity. That is your polar plot. And second one is minus 1 by n of x varying from 0 to infinity. So when the limit cycle occurs, there is an intersection point between these two. There are two locus, and the steep locus and intersects at some point. That particular point, that intersecting point, say for example, suppose if you say I have a system whose response is like this. Assume this is my g of j omega, okay, and assume this is my minus 1 by n of x. Assume it like this. And the direction of x is in this direction, and direction of omega is in this direction. That is omega 0 to infinity, and x is varying from 0 to infinity. Okay. So what is happening now? Some point it is crossing. This is the point at which it is crossing. Yeah. So this crossing point, I can able to measure what is my omega, at what value of omega and x. These two plots are crossing. So intersecting point can able to observe actually. So through this, I can find what is my omega and what I can measure what is my omega and what is my x. This is what that statement says. If you look at this, so that is what we call as predictions. So when you instead of going with only one plot, so far you drawn only one polar plot, because Nyquist is the combination of multiple polar plot. That means polar plot runs only with omega varying from 0 to infinity. Nyquist plot will vary with the three different regions, like we see here. This is 0 to infinity, and minus infinity to 0. And third one is this entire right hand side of this plane with the radius of infinity, right? So there are three regions. So normally we plot the infinity radius becomes a magnitude in the form of the origin itself. So only normally we plot two things actually. One is minus 0 to infinity omega, and second is minus infinity to 0. These are the two plots normally we plot, like what I have shown here. This is yeah, here it is there. This one is 0 to infinity, and this is minus infinity to 0. Basically, this is ulta to this, right? Ulta to this. So what we are seeing here, we are trying to understand once this crossing happens, right? I can able to measure this junction, right? This junction I can able to measure what is my omega and what is my x. This is the omega and x information limit cycle for the given limit cycle. So we told that there is a limit output oscillates at steady state like this. This information can be available, actually can be analyzed from this graph itself. This is what our whole objective was. This is what we are doing here. So because every time we were going with the simulation, hard linearity with the simulation, and understanding is difficult. So we are using an analytical method for predicting those values actually. So if you look at this now, the left-hand side shows that stable limit cycle, and right-hand side shows the unstable limit cycle. How we classify the stable and unstable limit cycle? Because here, this is my g of j omega, this response. This is my g of j omega, right? Omega is varying from this direction. and x is varying this direction. So direction is same direction we are keeping, and this is the running parameter is omega for gm j omega, and minus 1 by n of x, x is the running parameter. So this cross at this point. Okay, so the point we call as b x1 omega 1. So we are considering as a stable limit cycle point. So why we say that stable limit? Because normally we say that this g of j omega basically encircles this minus 1 by n of x plot. There are two locus, g of j omega and minus 1 by n of x, and g of j omega encircles minus 1 by n of x. That particular constant crossing point, the first crossing point, we call it as a stable limit cycle point. This is a thumb rule. And when you talk about the unstable plot, this minus 1 by n of x is encircles minus g of j omega plot. So the point at which it crossing, that crossing is called as unstable crossing. Okay, this is with respect to the same direction. Suppose if you are changing the direction, suppose if you are using let us talk about multiple crossings. Suppose I have minus 1 by n of x and g of j omega here, and but my response minus 1 by n of x is intersecting twice with respect to the point A and B. Suppose this is the point here, right? This point here, and this is the point here, at which, because this encircles this, so hence this A point is unstable point. It is visible here. And since this point, this duration, the traveling between A to B point, so this B point is a stable point. Your g of j omega encircles, that is inside. Your minus 1 by n of x is inside g of j omega. That's what it means. So your system is stable. It provides the stable point. So your question may be, what will happen if you have multiple points? Yes, there are possibilities. You can have multiple crossings, but if some system comes with the first stable crossing point, for example, and the system locks actually. So even if the multiple crossing points, if there are unstable points also available, once the system see that a stable point is available, so finally the system locked into a stable crossing point. So there is no point in worrying about unstable crossing point. Okay, so unstable crossing point, basically it's destabilized because your system provides instability, but stable crossing point basically provides a stable response, but it oscillates. On the other hand, we are looking at the response. Suppose if you are changing the directions, I have two crossing points again. I'm changing the direction. Omega is moving this direction, and x is moving the opposite direction. What will happen now? You can interchange this pointer. So here it envelopes here. So this point A becomes unstable point, and point B becomes stable point. So ulta here. Okay, that's a difference. What we see actually in the moment you are talking about changing direction, we will change the thumb rule. That's all. Let us understand the case studies. The first case study shows that on-off relay with the dead zone. Okay, so we have considered a simple process, and the process which we have considered is a k by s plus 1 times 0.1 s plus 1 the whole square. This is the plant we consider. This basically it provides a 3-pole system, and it comes with input nonlinearity, something like on-off with relay type of nonlinearity. So I'm giving some reference values. I'm changing the reference values and showing that what is the impact. Okay, and I'm also changing the delta. So these two, I'm going to change, alter, and see that what kind of response which we get actually, whether that one which you are getting from the response is an expected one or non-expected one. That we'll see. Okay, actually, whatever the work which we are doing are till currently we are working at all basics only. So these models are available in Nagarthan Gopal. And we extended for a control system design, and we published, I think this was in ISA transaction during 2015. Okay. With controller. Here I'm not touch upon any controller here because it's a kind of a 10-hour lecture actually I used to give for my MTech students and PhD students. So I'm giving only focusing only on non-linearity and based on non-linearity how that frequency information and magnitude information is predicted. Okay. So not going to deal with control system design, but this paper fully deals with the control system design. Okay, so but this basic block diagram you can able to see. This block diagram you can able to see the control system engineering by Nagarthan Gopal, digital control systems by M. Gopal. Yeah. So my plant is this, and I have a k here, right? This is the k here. I'm using two different values of k. The selected value of k is here as k equal to 5. And the second value is taken as k equal to 50. So what will happen here when we are using a k equal to 5 and the value of delta also we assumed the value of delta is something like 0.1 and m is equal to 1. Fine. So yeah, what is happening now? This is my plot, omega varying from 0 to infinity. This is minus infinity 0. You can assume only polar plot. We need to go with the inverter plot. We need to observe, because this I'm using we plotted by ourselves, because this things you need to draw by yourself. Okay. So because there are two plots, your Nyquist plot, whatever the command which is available in MATLAB, will work only for linear models. Non-linear model, it won't work. You have to write, and you have to get the data, and you have to plot the data in the Nyquist plot. Okay, so that's why we are getting a two different responses. One is this blue line represents my g of j omega, where omega is varying from 0 to infinity. This ultra response is minus infinity 0. That you need not worry about it. So then second one is your non-linearity. Non-linearity is minus 1 by n of x. It starts from here, because minus 1 by n of x is this 4m by pi x times square root of 1 minus delta by x whole square, and x is varying from 0 to infinity. But what is happening here is it goes like this. So when you start, it starts from infinity. I'll rewrite here to get more clarity in this. So it is actually in the negative real axis. Okay, that's what I plotted here. So what is happening? I'm just to make it to understand, I'm giving it like this. So it goes like this. When x equal to 0, right? It starts from infinity. Starts from infinity, it goes like this. And after some value of x, it will come back here. And when x is infinity, again it goes back to the infinity. This is what that function says. Okay, so that n of x, 1 minus 1 by n of x function. So when x is in 0, that starts with infinity, and when it is old, again it goes like this, and it goes penetrates, and it comes back here. So it means I have a response like this. Suppose I have g of j omega like this. So what will happen now, when during the time of penetration, I have 1x, but this is lying on the negative real axis in both the response. To make you to understand only, I'm splitting it and I'm showing it here. So it goes like this. My one is x1 and second one is x2. So there are 2 points at which that locus is crossing, right? Minus 1 by n of x crosses multiple times, because only it is going and it is entering into 0 point, then no problem, but it is going and it is coming back. That is what we see actually from the plot. So it means there are 2 crossing points. So first crossing point is x1 and second crossing point is x1. So correspondingly, you can able to observe that frequency values. Like here you can observe omega 1. Here I can observe omega 2. This point, right? So omega 1, 2. So we need to check which is stable point, which is unstable point. That is the first point we'd like to understand. Okay, and when this is plot with respect to k equal to 5. And second one, just we change the value of k gain, feed forward gain as 50, and we redraw that response. When you look at this response, my g of j omega is this, and minus 1 by n of x plot is this. If you look at this is also penetrates, and it's coming back, but it penetrates more. This is the thing I would like to say. This penetrates very less, and this penetrates more. That frequency information, 11.12 radians per second is given, and 11.1 radians per second at this point, crossing point. That also information is available from the plot. Okay, other information like real point to minus 2.03 in case of k equal to 50, and in case of k equal to 5, it is 0. minus 0.202. This is the output response of the system. So when you are simulating the response with nonlinearity with the different values of k, so I have got the response. This is purely simulation. What you are seeing is two different platform I am showing you. This platform is only just magnitude. We are drawing the Nyquist plot, polar plot, and then we are plotting minus 1 by n of x, superposing the minus 1 by n of x, and we are finding the information like frequency information and magnitude information. This is one. And second one is we are keeping the nonlinearity itself in the loop, and we are simulating it using the MATLAB simulating, and we got the results as this for different values of k. First case k is 5 and delta is 0.1 is considered, and second case k is 50. So the response is like this. So we also we can also measure the magnitudes, that is magnitude and the frequency. The frequency also we can able to measure, right? So we need to check whether whatever the value which we obtained through this is matching with the response which we got it through simulating them. So I have tabulated here whatever the explanation I have made. crossing point with respect to this k equal to 5 is minus 0.202. We already told that. Minus this one, 0.202. And here minus 2.03 when k is 50. It is done here, k equal to minus 2.03. That information is available to us. So this is from the graph, right? And second one is, as we told, there are two times it intersect, x1 and x2, right? So with respect to x1, definitely it is coming from outside. My g of j omega is here inside. So definitely it is that first crossing point is an unstable crossing point that we have seen, and so this crossing point we need not take care of. So here also same thing happened. First crossing point is unstable crossing point. We need not worry about the first crossing point. So only second crossing point, actually that condition satisfies, stable condition satisfies. So it provides the stable limit cycle condition. So this information we got it. When you look at this simulation system, right? We put the hardware nonlinearity in the loop and we simulated. So what we got, actually, we got the response as this. From this response magnitude, what we got is 11.2 and sorry 0.2233. This is 0.2233 and frequency is 11.2. This is what we are saying, 11.2 seconds radians per second. And in case of k equal to 50, the information what we obtained actually from the graph, from the response, I would like to say 2.635 and 11.1. So if these things are matching, already matching we had seen, and if you look at this and this information is also very close, 2.362 and 0.22633. And in case of k equal to 50, and we found was 2.6 and 050, 2.635. This is almost close to each other. So we assume that our prediction is predicted value is correct. So our model also validated. This is what normally we say or we see actually based on the results. But we tried with some experimentation. We started doing experimentation after this values obtained. We introduced, we changed from 0.1 to 1. 0.1 to 1. So other values are same, k equal to 5, k equal to 50, two different experimentation we performed, but only instead of delta equal to 0.1, we changed to 1. So some 100% just be increased, and m also constant 1. So what was observed actually from the Bode plot, the Nyquist plot, if you left hand side, if you look at it, k equal to 5, there is no penetration at all. It is not at all penetrating. So if it is not penetrating, means what it indicates, actually there is no intersection point. That no intersection point should indicate that there is no limit cycle. This is what our observation. This is what our idea is, right? Our point is. If you look at the second case, when the moment you are increasing k equal to 50, the same plant, but only delta we are keeping delta equal to 1 instead of 0.1. So what is happening is there is an intersection point. Some information also we have observed. So this is our intersection point. Some information is observed, 11.1 radians per second with minus 2.02 magnitude. Right. Okay, we'll go to the simulation and see. This is one observation with respect to our Bode plot. Nyquist plot. So Nyquist plot clearly state that k equal to 5, there is no limit cycle because there is no intersection point between this minus 1 minus x and g omega plot. But with respect to k equal to 5, when k is 50 and a crossing occurs, definitely limit cycle occurs. If you look at this, actually k equal to 5 and delta equal to 1, right, with respect to unit step input. So the unit step input provides you something like some response here. What you see here, 0 response here, and for both k equal to 1 and k equal to 5 and k equal to 50. And when the moment you start increasing the magnitude, step magnitude 1.1 to 1.5, it changes. Now you see that there is a steady state oscillation. Even though there is no crossing point, right? There is no crossing point because of the change in magnitude. This one instead of 1 to 1.5. Started providing this. The system also start oscillating when k equal to 50. You look at this as continuously, k equal to 5, 1. I'm changing from 1.5 to 2. I can able to see this. But what should happen? It should not happen in any oscillations. It should provide us zero oscillations. But it doesn't happen actually. When you are increasing the magnitude to 5, so 3 to 5, 2 to 5, you can able to see visualize the oscillations. When you are increasing the value of 5 to 8, there is no oscillations. No oscillations, no limit cycle. as we discussed in the previous first slide of our presentations. So initial conditions and input magnitude also play a major role when you are dealing with non-linearities. Can be input or non-linearity or output non-linearity or maybe sensor non-linearity, but you should be very careful actually when you're dealing with it. So these false predictions, yeah, here it is happening is a false prediction. We did with this analysis, but finally we found that it predict actually it couldn't able to predict the proper values because when with condition changes, this is also changes. So what we should believe is we should believe only with simulations. Simulation and this is a supporting tool actually for checking these simulations because all simulations cannot be carried out fully, or maybe sometimes it become very complex. This could be very simple approach for approaching or dealing with such systems with nonlinearities. This is our observation. This observation is actually represented actually given here. Another example which I have considered here as a servo system with backlash. So this is a practical problem actually which we consider because most of the labs which we use to have precision models, this precision motor systems used to come as gears and drive belts. So the gears and drive belts basically introduces a backlash kind of these things, and this motor along with this amplifier and motor along with this that can be written as a transfer function GFS, and your nonlinearity is gear nonlinearity, and that introduces backlash kind of nonlinearity. This is also available in Northern Cobalt textbook, and the extended version actually we published actually in this nonlinear dynamics. We also here we used control system design for such plant. So because we worked with very basic studies actually, very basic basis of that. So it is a very basic problem, and it is available in all the textbook. Only we think is we proposed a new design, a novel framework actually here. It's written to design and compare limit cycle minimization controllers. So various controllers we defined. We define P, PI, PID controllers, and we also define some kind of fractional controllers also into account actually during the time of our studies. So we are not going through the control design as we discussed, and we are going to showcase only the response. So we know that GFS is this, and my nonlinearity is this. As we discussed, we have a nonlinearity comes with the function J. And if you look at this red line, red represents -1 by n(x), and blue represents G of j omega, and it intersects it twice. This point actually is unstable point, as we already told with respect to the rule. So unstable limit cycle point. So we can ignore this point, and this is provides a stable limit cycle point. This because this encircle G of j omega encircles -1 by n(x). So this is information. So my oscillation is 1.59 radians per second. My real part is -1.242. This information. So you need to plot these two graphs, and you need to find the information. So check the crossing point or intersecting point which is stable. So that information, from that we can extract those values. This is the closed loop simulations which we obtained. This is with respect to nonlinearity input, and this is the red color represents your system output. So whatever explained, it is told here. The first intersection point is here, and second intersection point is here. And with respect to the response, your second intersection point is taken. So this is I provides unstable. This provides a stable limit cycle point. This is considered for our response. So by doing this, our response is final response, closed loop response supposed to be 0.95. If you look at this, I have put a single table to just give the consolidated values of the magnitude predicted values with respect to graphical approach, that is discrete function method, and the closed loop simulations which we carried out through MATLAB. So in case of backlash, other things we are seen in detail. In case of backlash, if you see that this is y is x minus h, that is 1.03, and this is output response which is obtained from the simulation is 0.595. So almost, if you look at these responses, almost it's all close to each other. There is some difference will be there. The difference because of this approximation, because we are working only with the first order harmonics. Sometimes there is a possibility of entering into other harmonics also. But some since our control system design provides you low pass filtering effect, almost all higher order harmonics will be suppressed. Still, there are possibilities. Due to the possibilities, this kind of small deviation can happen. But sometimes large deviation happens because of higher order harmonics with high magnitudes. So what we have done actually during the past was we introduced all the discrete function we modified actually, because I have modified one of my students actually did it. He modified with the help of a signal processing approach. and he completely he revamped instead of going with only fundamental harmonics, that is first order harmonics, we introduced third order, fifth order, and seventh order, and we derived these expressions, and we got the results, predicted results very close, very close. But this information normally we used for design of controllers, but we have some challenge actually hinges with respect to that, because only certain limited nonlinearity only we can able to handle it. And there are other nonlinearities, because with respect to the literature, they say that measurement and system provides you some kind of 24 nonlinearities in the loop. So this, whatever the method we propose, the signal processing method, is applicable for only few nonlinearities. We are not able to generalize it, because generalization is very much important actually. So when we are dealing with such nonlinearities, actually for engineering applications, so we are not able to. We are not able to do with the generalization. We are working with only specific, but we are right now we are working with generalized. How to make it generalized things. Basically, it's an extension of the describing function, because describing function is applicable only for fundamental harmonics. We are using with some kind of approach. There is no name we call it as, and we are name it as just modified describing function. That's all. Okay, so once you know this, we can able to do that. Like just I would like to demonstrate with the controller. So if you say that I have a plant, suppose if you say I'm giving only idea for this, because this presentation contain only prediction alone. So this is my real part and this is my imaginary part. Suppose if you say I have G of J omega, this is planned without any controller, right? And my 1 by n of x, I would like to draw then minus 1 by n of x. So the direction of 1 by n of x also important actually, from where to where it is going, right? 1 by n of x. X is varying from 0 to infinity. So I'm making the direction as this. For this, for G of J omega, the direction is plotted like this. This is my G of J omega. Suppose if in the moment you are introducing a controller, so what will happen now? Your G become G times GC of J omega. Hope all of you agree. So it means I have a plot. I have different plots. I may have a plot like this, or I may have a plot like this, or I can have a plot like this or like this. So with the different controller, maybe C1, C2, C3, C4, with the different controllers, I have different response. I'm sure that you can able to follow it. So my GGC by have a different controllers. Assume some trial controllers I'm using. With respect to some controllers, PI controllers with the different parameters of KPK, KD, I have different responses. So what we told, and the one which crosses intersect, that information is nothing but x and omega. So you see that x and omega changes at this first point over G1 controller, my x1, maybe I have maybe say x2, this is x3, this is x4, this is x5. But this is the one, the controller one provides the minimum x. I'm using ascending order, so it happens to be C1 and here, and my controller one provides you here x2. This could be the minimum values. Okay, this controller basically we obtain whatever, you can refer those papers which is cited there. Normally we use some kind of performance index that has to be minimum. What is our performance index? Our performance index is x. X is our performance index. So x should be minimum. So we found controller KPK KD through the optimization method. We use actually here we are using actually fmin_con. There are two functions actually which are available. We are using fmin_con, a function minimum to be minimum with respect to constraints, function to be minimum with respect to just without any constraints. But if you look at this graph, the one which provides minimum, that will pick actually. That will pick by the function fmin_con. So this is the way we, because we should also ensure the stability, right? So that's why we used to write stability conditions along with this minimization function. So that's why we use fmin_con actually, function minimization to be minimum with respect to the constraints. So finally we got the controller as this. So that controller provides you minimum x. So this is the way now basically we design. So this is I'm just elaborating what is done actually with the control design. It's a different topic. Normally we spend more time on this control system design actually. So these are the references with respect to the discussions which I have made today. So as I already told you, basic books, control system books, you please refer Managrudan Cobol, or you can refer M Cobol book, digital control system. All these whatever the information which is presented here, they are available actually. Even some extension also available there. Even there are a few more non-linearities he put, and he derived the expressions. And the second paper, which is actually Rangaswamy Sridhar, Professor Rangaswamy Sridhar, he has actually done a wonderful work in non-linearities. And he made, because so before 1960 actually people deal with the non-linearity separately with the separate conditions, but he took all the non-linearities into account and he made a general non-linearity. So finally he presented one non-linearity with one non-linearity, how that all 24 non-linearities can be done. So one derivation can be useful for making getting any kind of non-linearities like backlash, anything you say through by assuming 0, 1 and etc. you can able to get the final derivation. So he made a wonderful work and presented into IEEE transaction on automatic control in the year 1960. And we also refer the book. Actually, our Bible is actually Gulp actually, so you can also refer. This is freely downloadable. You can also download the work, and basic things where they normally give single input, single output conditions. And we also work with multi-input, multi-output conditions. This book is very useful for multi-input describing function models. Okay, so this is what the whole picture of the work which I have presented today. Now you can have a question session. If you have any questions, I'm ready to answer. Thank you.
From participants? Thank you, sir.
Thank you.
Participants, if you have any question, please ask. Anyone from participant? Okay, anyway, you have very nicely explained, sir, all the details of non-linearity. I hope that all the participants will get benefited from this lecture. You try to explain with the help of examples also, case studies also you discussed. Thank you for joining us.
Yeah, thank you very much. Thank you, ma'am. Thank you for the opportunity. Thank you.
Thank you.